to cover the signed rank test. This is another non-parametric test that can be used as an alternative to a one-sample t-test or a paired t-test. Remember that the conditions to use a t-distribution to make inferences about a single mean or the mean difference if you're working with paired data are that you have independence between observations and that you have a nearly normal distribution, which can be relaxed for large sample sizes. And when we're thinking about, well, what can we do if the sample size is small and the distribution is not nearly normal? We saw in the last video that we could use what's called a sign test, but that the sign test throws out a lot of information and isn't very powerful. We'd like to use something else that uses more information and gets better power, but still doesn't require this normality assumption. The Wilcoxon signed rank test is going to give us that option. The signed rank test tests hypotheses about the median. The null hypothesis would be that the median is equal to some hypothesized value m sub 0 versus an alternative that the median is not equal to m sub 0. We're going to use the same example that we used in the last video because it's a test that's appropriate for the same situation. Remember, in this example, we're looking at a microbrewery that had labeled the alcohol content of their double IPA as 8% alcohol by value. And they are using a random sample of 8 batches of beer to test to determine if there's evidence that the alcohol content is mislabeled. So the hypotheses here are that the median alcohol by volume is equal to 8% versus the alternative that it's not equal to 8%. So the sign rank test works this way. For each data value, you calculate a difference between the data value and the hypothesized median. So that's similar to the sign test. Then we rank the differences from smallest to largest. We find the sum of the ranks that are associated with positive differences and the sum of the ranks that are associated with negative differences. And then the test statistic, which we call t, is going to be equal to the smaller of those two sums. And we'll use a table to decide whether or not the hypothesis is rejected. And finally, once we know that, we'll make an appropriate conclusion in context. So the data for our example is shown here. And remember, the first thing we have to do is calculate the difference between each of those values and our hypothesized median. So here we do that. We calculate a difference for each one. Now we're going to rank the absolute value of the differences from smallest to largest. So I've calculated the absolute differences in this column here, and I'm going to rank them. Now if I look, I've got two differences that are both 0.1, and those are the smallest differences. When I have two differences that are equal to each other, I take the places that they're going to hold, those would be the first and second values, and I average them, and I give them both the rank of 1.5. And then I'd move on and say, okay, what's next? Well, let's see. In the third and fourth smallest places, I've got 0.2. So I need to rank those equally also. So let's see, those would be the third and fourth. So average of those two places would be 3.5, and so on. And I continue to rank them as I go. Then I find the sum of the positive ranks. So if I look, the positive differences, the 8.1 gave me a positive difference, the other 8.1 gave me a positive difference, and the 8.3 gave me a positive difference. When I add up the ranks, I've got a 1.5 plus 1.5 plus 5 gives me 8. And similarly, if I add up the ranks associated with negative differences, I get 28 for the sum of the negative differences. So since t is my smaller sum, t is 8 here. The next step is to use a table to find the p-value. Here, remember, my sample size is 8, so I look down the left-hand column of my table till I find number 8 for my sample size, and then I look over and I can see that my t is a t of 3 would give me an alpha level of 0.05. A t of 0 would give me an alpha of 0.01. And so since my t is bigger than this, I don't know exactly what the p-value is, but I know that it has to be bigger than 0.05. Remember that my hypothesis was that the median is equal to 8 versus the alternative, the median is not. The p-value is greater than 0.05. What this tells me is that there's not strong evidence that the median alcohol content among all batches of this microbrewery's double IPA differs from 8%. To implement the signed rank test in R, we use a function called wilcox.test. Here my variable name is ALC. The alternative that I'm interested in is two-sided because my alternative was looking for a two-sided test, and my hypothesized value is being specified by mu is 8. When I use this test, it calculates the test statistic, which it calls V instead of T, and the p-value 0.1824. And it tells me what my alternative hypothesis is. Notice that it's also giving me a warning message here. The p-value is approximate as opposed to exact when you have ties in your data, so that some of the ranks were tied. Don't worry too much about this. It just means that the p-value is a little bit more approximate than it would be otherwise. Let's look at how to modify this for a paired data type of situation. Here I have a situation where I have 9 subjects. They each took 2 quizzes, and I have their scores on each quiz. Since it's the same subjects taking each quiz, I can calculate the difference for each subject. Once I calculate those differences, I rank the absolute values of the differences. I would calculate the sum of the positive ranks and the sum of the negative ranks. Since my null hypothesis is that the median difference is equal to 0, I don't have to worry about subtracting after I calculate this difference, the hypothesized difference, because the hypothesized difference is 0. So I simply calculate the difference in the 2 quiz scores, rank those, and find the sum of the positive and negative ranks. Here T is the smaller sum, which is 5. And again, I can use the table with n equals 9. My two-sided p-value for t equals 5 is approximately 0.05. If I were to do this in the R, I'd have my 2 variables as the quiz scores. So quiz 1, I assign those quiz values. Quiz 2, I assign the others. And then I can use the wilcox.test again. Here I put in the 2 variable names, one holding quiz 1, one is quiz 2. I specify that my alternative is two-sided, and then I write paired equals true to tell it that I've got paired data in these quiz 1 and quiz 2 variables. And my hypothesized value is mu equals 0. And here it gives me my p-value of 0.04125. Some of the strengths of a signed rank test. One is that it does not require any assumptions about the shape of the distribution, so it's useful even when you don't have data that are nearly normal. Another strength is that it is a more powerful alternative to the sign test, which you might otherwise choose in this situation. Some weaknesses: it does still ignore some information about the absolute magnitude of the differences, but by including the ranks, at least it includes more information. But because it does still include some information, it is less powerful than the t-test if the data really do come from a normal population. So you will sacrifice some power if the data are in fact normal. So you don't want to use this all the time. You want to use it when the conditions aren't met. All right, that's it. Have a good day.